So let's look at number 17 in Achieve section 4.2. We're going to find the max and minimum of this function on the interval from 0 to 1, dealing with a trig function. So be careful that, any evaluations you do with calculator, for instance, you're in radian mode. And this function is continuous on the interval from 0 to 1. Tangent function does have vertical asymptotes. Remember, at pi over 2, negative pi over 2, and so on. But pi over 2 is 1.57, so we are safe. We're not in that interval, okay? Or we're just going from 0 to 1. So on that interval, this function is continuous. Okay, so again, what do we need to find maximum? We need to check the value of this function at the endpoints of 0 and 1 and at any critical points on this interval. So the hard part is finding the critical points, okay, on the interval. So how do we find critical points? We find the derivative. So you have to remember how to find the derivative of the tangent function. Remember, that's secant squared. Derivative of 14x is 14. So there's my derivative. So the derivative is, first of all, it's never undefined. Now, the secant function is undefined when cosine of x is 0, because secant is 1 divided by cosine. And cosine is 0 again at pi over 2, just like with tangent. In fact, secant and tangent have the same location for their vertical asymptotes. Again, since x is on the interval from 0 to 1 and pi over 2 is 1.57, we're not going to hit any vertical asymptote. So this derivative is never undefined on this interval. But it is 0 when what? Well, it's 0 if 14 is equal to 7 secant squared x, right? If I just add 7 secant squared x to both sides, I get this equation. Divide both sides by 7 gives me secant squared x is 2. Remember, secant x is 1 over cosine x, so secant squared is 1 divided by cosine squared. And then since this is equal to 2, if I do the reciprocal of both sides, cosine squared x is a half. Taking the square root, in general, we take plus or minus, right? So we get plus or minus the square root of a half, which is plus or minus 1 divided by square root of 2, which if you rationalize is plus or minus square root of 2 over 2. Should be a familiar looking number. Now, we're actually only going to consider the positive root because on, again, the interval for x being from 0 to 1, for x values between 0 and 1, the cosine function is always positive. Here's the graph of the cosine function from 0, pi over 2 pi to 3 pi to 2 pi, right? One complete cycle. And it's positive between 0 and pi over 2. Here's 1. Remember, pi over 2 is about 1.57. So from 0 to 1, we're just on this interval, right, from 0 to 1, and the cosine function is positive, so it cannot be negative. So the only thing we're looking for is when is cosine x equal to square root of 2 over 2. So, of course, we have our unit circle available for us on the test. Remember, the cosine is the x coordinate here, and it's square root of 2 here, also down here. But this value, of course, occurs at pi over 4, and pi over 4 is less than 1 because pi is 3.14. In fact, I've got pi over 4 is 0.785. So that is on the interval from 0 to 1. So this is a critical point on that interval. And that's actually the only one. The only other, there are infinite number of values where the cosine is square root of 2 over 2. It occurs down here at 7 pi over 4, but that's more than 1. And of course, if we add any multiple of pi, which is 2 pi, to either of these values, which is 6.24, then we're going to be, obviously the cosine of that value will be square root of 2 over 2, but that x value is bigger than 1, and so we're not going to include it. So there's infinitely many values, again, because the cosine function just continues to go up and down forever. But just at pi over 4, where it's equal to the square root of 2 over 2, is the only critical point on the interval from 0 to 1. Okay, so there's our critical point. We have our endpoints. Now we go back to the original function, not the derivative. Make sure you go back to the original function, not the derivative, back to the original function, and plug in the value of the endpoints and this critical point. So plugging it into this original function gives us this, okay? For 0, of course, tangent of 0 is equal to 0, and so I get 0 when I plug in 0. When I plug in 1, I get tangent of 1. Now, tangent of 1, I don't know what that is. You can use your calculator to approximate, but I get -7 tangent of 1 plus 14. So there's the exact value, and using a calculator, making sure you're in radian mode, that's about 3.098. If I plug in now at the critical point, pi over 4, I'm going to use the exact value, not the rounded value, pi over 4. Now you have to realize tangent of pi over 4 is equal to 1. And again, we go to the unit circle. Most of you already know that, but tangent, remember, is sine divided by cosine. So sine divided by cosine here is 1 at pi over 4. So tangent of pi over 4 is 1. And this is 14/4 or 7/2. So -7 times 1 gives me this. This is the exact value using a calculator. That's about 3.996. Okay, so the approximations are important because we'll want to know which one is smallest and which one's biggest. Well, the smallest is 0. That's our minimum. The largest is 3.996. So this value, the exact value, that's the max. And this is what I want you to do on the test. I want you to give me the exact value. Okay. You certainly want to get the approximation so that you can see which one is the biggest, but you have to give the exact value. And it might look kind of weird. It might be, -7 tangent of 1 plus 14, because tangent of 1 I can't evaluate. Don't leave it as tangent of pi over 4. I do want you to evaluate that. You should be able to evaluate any trig function at any of our common measured values, right? Pi over 6, pi over 4, pi over 3, pi over 2, and so on all the way around. Okay. All right, hope that helps with this one. Little tricky sometimes with some of the trig functions, but there is, again, this, the same idea though. Find the critical points, check the value of the function at the critical points and endpoints. That will give us the max and min on the given closed interval. Okay, hope this helps y'all.